All right, so all right. So we have a problem here. We should send him a ticket. This is the light bulb seems to be burned. All right. Yeah. So again, guys, look here or there. I didn't know. Not something I can do a solution for very quickly, but let's get started anyway with what we have. And so today we will be resuming from the last recording. The last recording was about neural LLMs, neural network-based language models. So we'll talk about like a few architectures of neural LLMs, and we'll talk particularly about deep RNNs, bi-directional RNNs, and multi-layer RNNs, and how we can use those for different exercises, for like machine translation, for instance. Also, we covered encoder-decoder. Encoder-decoder is very important. This is going to be in the midterm, something that you need to pay attention to. And so today, we'll talk about, again, this is more of an NLP class. It's not really anything to do with visions or image modalities. And so you might be wondering, why do we care about CNN-based models for text representation? And the answer is that oftentimes you not really care about something specific for representation, specific to the language. It is anything that can be done that is cheap, very quick, cheap, efficient to implement. And then the representation, higher level representation, is going to be the learning component, that is going to be the RNN, is going to take care of the language characteristics. But the initial one, like the CNN, is going to be used for just feature representation. And so that's why we bring it here. And it's very important for applications like translation, machine translation, okay? This is what the outline will look like. So we'll talk about what are the limitations of RNN that, what's going on here? Thank you. Okay, all right. So, CNN, as I said, it's not really by design for languages. It is by design for textual data, for image data. It can be used to extract features from image. They preserve the spatial characteristics of a given input. And so they're not really designed for languages. But then why do we have them here? So I said earlier, we have them because we want to have some feature representation. But actually, there are some issues in RNN that make this one particularly nice. So we'll talk about the limitations of RNN. We'll talk about CNN motivation, phrase level convolutions, some mechanics, technical details of how CNN works for our domain, with some concrete example. We'll talk about CNN architecture, and then the actual application that we care about in NLP, which is going to be sentiment analysis and text classification. Okay, so without any further ado, we have the objectives: understand the limitations of RNNs in capturing phrase level and long range dependencies. This is a problem that's going to be recurring for anything that is to do with RNNs and any flavor of RNNs. And RNNs, LSTM, GRU, bidirectional RNNs, multi-layer RNNs, all of them have the same problems. Then we'll motivate for CNNs, for sequence modeling as an alternative. Then explain some of the technical details of CNNs, like 1D discrete convolution for text, and how the filters and different kind of parameters of operation of CNN would work in that space. Analyze the rule of pooling, like max, average, and K-max in feature aggregation. Then CNN architecture for sentence classification, and then evaluate the strengths and limitations of CNNs in this space. Any questions? All good? All right. Tell me the truth. Weren't you really happy when I was away? You don't have to be here. Somebody was happy there. Yeah. Not have to show up. Yeah. I have some we will divide this group into two, this class into two groups. The loyalists, those who took my class before and then just came here back again for the punishment, and like the newcomers, newcomers who are not used to this time. Okay, so let's go over the what are the problems with RNN. Again, like the way that RNN works is that you start with a given input here. Let's say this is going to be the embeddings that we have, and then you feed those E's into the W's and get like some immediate representation. It's going to be the H's, the hidden layer values. Make sense? So with X's can be embedded with capital E to get you like that small e, E1, E2, E3, E4. And then you push that E into a WE, like the weight matrix of this neural network, to get a hidden output. And then that hidden output is going to be then scored with the function U, adding some biases to get you the final output is decoded. That's how it works, right? So imagine that you have, and here I'm just like making it simple. Imagine that you have the numbers. This is the embedding. And this embedding is fed with W to give you some value that is going to be H. H1 is going to feed into H2 with the input, with the embedding. And H2 is going to feed into the H3 with the embedding, H4 with the embedding, then H5. And if this is to be viewed as a language model, again, what is a language model? It's filling the blank, predicting the next word based on the words so far. So let's say that we have 4 utterances, a sentence of size 4, and we want to add the last word here. So it's going to be the result of decoding the output coming from this hidden layer, right, with the function u. Good? Then you can imagine that a great focus is going to be on the weights in this layer, more than in this layer, more than in this layer, more than in this layer. So this is a recency problem, that the last part of the utterances is going to be more significantly emphasized in the output, right? So that's a problem. That's a huge problem. So to put that, RNN process sequences one step at a time, updating the hidden at each step. The hidden is going to be like, H1, H2, H3, H4, and then H5 is the final one that's going to be scored. Okay. So it's going to be basically having this issue of prefix dependency. And this sequential dependency means that the phrases without strong prefix context are oftentimes not well captured. So the example, the input, the book that I borrowed was fascinating. RNNs may struggle to connect book with was fascinating if immediate words dilute the meaning. Okay, so going all the way from the beginning to the end, and unless you have like really strong prefix characteristic, you will not be able to tie this word that you're going to predict with something that is a little bit farther, because there is this sequential structure where you calculate like the hiddens depending on the previous hiddens. So like there is a distance between this, right? So this is one problem. The other problem is actually the recency. So the recency, questions? How come? What are my slides saying in the why? Show me what you have in the slides. Are you opening the slides? No. Are you opening the slides? Okay. This is 10. We have to go to 11.
Oh, we don't have 11.
Oh, I not published it. Okay. Sorry for that, guys. This is supposed to be like module 4. So 9 and 10 are already recorded. So this is 11 and this is published. So you're really not like keeping track of what we are doing here, right? So this is telling a little bit, right? I'm out for two lectures, right? And so last lecture we had is number 8. Number 9 was supposed to be on the whatever that is, the 7th, 8th, 11th, right? 6, 7, right? And then we have 10, which is the second lecture, and this is 11. So we have 2 lectures that are recorded. Okay, so yeah, I should publish that one. I'll publish it immediately after I get out of here. So but this is bad, isn't it? Because the assignment is shared with that, right? You should guys complain about the right things, not about like me recording the lecture. So okay, the second issue, this is the first one. The first one is that there is a strong prefix dependency. The second one is the recency. So in this example, I explained it earlier, your output, eventual output, is going to be dependent on a bunch of prior steps, and the weight of the step as for its significance for the output that you have, immediate output that you have, is going to be proportional to how far it is from the output. So HT minus 1 is going to have larger contribution than HT minus 2, then H2 minus 3, than H1, for instance, in this example. And so this is what we have. Our analysis process sequences one step, so this is the prefix. This one is the overhead of the recent tokens. So the final hidden state is going to be disproportionately represented by the last few tokens. And so early tokens in the sequence fade in memory, leading to an implicit recency bias. And this is just like in general, without any problems we have with RNNs. If you watch the recording that you guys have been pushing me to put out, then you will find out that we have a lot of problems that would make this particular issue even more significant. And that would be like, the vanishing gradient, for instance, right? So because you have a small weight here lower than 1, and when you multiply them by, say, for example, something that is small, there's nothing small here, but like the weights here, they are small, then the precision of the value is going to diminish, right? And so you multiply a large number of those. This is going to be Rn. So you can imagine that it's going to be the equivalent of raising the matrix W to the power of T, where you have T number of steps for learning, okay? So raising a small value, 0.5, for instance, to the power of 5, 10, whatnot, is going to give you a diminishingly small value. When you do like the backpropagation and derivatives, those values are going to lose the precision. And so you will not be able to capture the impact of the first step at the last step, okay? So this is the sensitive problem. So the example input, the performance was excellent despite slow start. RNNs may overemphasize slow start in its final representation, then the performance was excellent, okay? So this is going to give you a problem. The last one is the aggregation, which is the softmax at the last step. So the softmax aggregation at the output layer is going to be computed only at the last time step. It's not calculated at any of those intermediates. And this means that all the previous words only contribute indirectly in a probabilistic sense through the hidden state. And the final output can misrepresent in a way sentence meaning if a crucial information appeared earlier. So these are problems. What is the implication of this problem? Well, as a result, RNNs will struggle with the long-range dependency, very naturally, right? So if you are saying that the last couple of steps, last couple of tokens are more emphasized in the output, then your RNN is going to struggle with the capturing how the one before, the one at the beginning would contribute more or less to the final output, okay? So this is one problem. So RNNs will struggle with the long-range dependency. Imagine that you have like some clauses in between for a long utterance, and that will create artificially maybe a long sequence dependency, and the likes of RNN will struggle to capture that dependency. Alternatives like transformer models address this by using self-attention, which considers the entire sequence at once. This is great. This is wonderful, transformers. This is like state of the art 10 years ago. And we will use that actually down the road. We talk about LLMs. And by the way, transformers are described in the previous recorded lecture. This is very important, encoder, decoders, transformers. It's good, but if you know anything about self-attention, what self-attention is basically is going to be a bunch of parameters. It's a matrix. We talk about like LSTM. LSTM is attention mechanism. You have a bunch of parameters. It's going to be 3 matrices that you have to process the input X with. GRU is something else that is nice that addresses some of the problems of attention. It's going to be 2 matrices. It's large. With self-attention, it depends on your design of self-attention. You can have multiple hidden self-attention, so you can have arbitrarily a large number of matrices that you can add to that, and it's not going to be efficient, not for this particular goal. So what are the other alternatives? Well, because I'm going to teach this, it's going to be CNN. All right? It can be anything else. It can be a lot of other things. There could be a lot of other alternatives, but CNN is one of them. Okay, so CNN for sequence. Any questions, by the way? Any questions? Good. Okay, so your question? You don't have a question? Okay, you look sleepy, man. All right, and it's my birthday. So CNNs for sequence modeling. So how many of you are familiar with CNNs? Not the news thing, but CNNs, the scientific thing. 1, 2, 3. You are a shy crowd. 4, 5. Okay, not many. Okay. So here I'm going to teach you CNN the way I taught it to my high school son, and no disrespect, it's just because CNN, if you like, look at the mathematics of CNN, convolutions and operators and operator selection and whatnot, it might seem overwhelming, but deep down, it's a very simple process, and to be honest, it's very beautiful. First time I learned about convolutions actually was in control systems in my undergrad. And since then, I just like the simple representation, not the integral and operators and whatnot. So it's very beautiful. Let's go over it very quickly. So CNNs are useful for tasks where in our domain where phrase level features are important, and you not really care about the deep features, but you have an overall feature, an overall representation. So you do not want to have deep semantic, but you want to have just like high level semantic. So, and that can be in phrase level features that are important in the likes of text classification. So you want to have a class label for the entire text, like 1, 2, 3, 4. That's a class label. Or sentiment, positive, negative, hateful, not hateful. So you do not really care about the underlying deep semantics, but some sort of semantics, right? And that can be in the classification domain. They are very efficient if you are concerned about efficiency. In the case of RNNs, what do we do in RNNs for language models? I mean, forget about language models. RNNs, we want to use them as feature representation, feature extraction system. What do? We have to build a model. We have to get those Ws. We have to get those right biases, Bs, right? We have to get those right biases. With LSTM, 3 of them. With GRU, 2 of them. Self-attention, that many of them. With this one is just very simple. It's as if you are doing more or less n-grams in a more elegant way. And remember, n-grams does not require really any training. Just like go over the entire corpus and then slice it and dice it and just do calculations for how frequently a given utterance appears, right? So similarly, CNN gives you this efficiency. So if efficiency is a concern, this is where you have to work. CNNs are more parallelizable than RNNs. We'll talk about that in a second. If you have, like, say, for example, fixed length context window, which suffices with this kind of domain. So you don't have to worry about like long context to be able to capture some characteristics of the given underlying language for feature extraction. However, for tasks requiring long-range dependencies, transformers remain the best alternatives to RNNs. We should not go there. And here we are going for this only because our applications and kind of make that compromise. They sacrifice whatever the RNNs give you as a plus for the efficiency that you have here. And the example that we have here are going to be sentiment analysis and text classification. Any questions? This is why it's good. It's great. It's nice. It's fancy. So the main idea of the CNN for NLP, we have the CNN for text processing. Key concept: instead of processing text sequentially like RNN, like starting with the first utterance, second utterance, then utterance for utterance to get like the prediction. Here, CNN compute a vector representation is going to be for the given sentence a vector representation, as if it is the n-gram representation, right? Okay, what is the n-gram for a given sentence? Is going to be the frequency of like character tokens, characters or words or whatnot. Here is going to be some sliced and diced representation of that frequency. And so this enables parallel feature extraction at different positions in the input. If you can view that those are somewhat independent kind of counts, then you can say, I start from the beginning of the sequence to middle of the sequence. I'm going to have like one parser that does the calculation. And then from the middle to the end, another parser that does the calculation. And I'll have the features twice as quickly as if I'm having like a single pass on the sequence. Does it make sense? Okay. So what you have like here is going to be say the example I have here. I like to explain that with the example. So tentative deal reached to keep government open. The CNN will extract the following n-gram, where n equal 3, where the window size equal 3 for feature vectors. Is going to have tentative deal reached to keep government open. You can imagine that as like what the CNN will give you. Now I'm just like being silly a little bit by saying that this is what CNN will give you. CNN does not give you this, but you can imagine that this sliding window where you just calculate features from this. This could be like a whole bunch of features, a whole bunch of features, a whole bunch of features, but a sliding window sort of thing. Okay, I'll show you like how we do that calculation. So what is the good thing about this? It captures phrase level features, like regardless of the grammatical correctness, does not really care about grammar. Works in parallel, unlike RNN. So you can, for example, have multiple threads, and one of the threads would work on tentative deal reached, and one works on to keep government, and one is like on keep government open, and you will not basically affect the overall feature, because the overall feature is going to be a combination of all of those. Make sense? Good? Understandable? All right. And you know, the problem with that is that it is not like, because it does not really care about grammar, then it's not linguistically or cognitively plausible. So fixed window ignores sentence structure, and the feature extraction is position invariant. Does not matter where the phrase appears. This is good or bad. Is it good or bad? For the application that we have, it does not really matter. We care about only just sentiment. Like, is it positive, negative? I don't care, like, you know, how grammatically it is, right? How grammatically correct it is, right? But, you know, this is to highlight that for certain applications that care about deep semantics, this might not be the right solution for it. We still want to do like attention-based mechanisms like transformers. All right, so how things would work, how to aggregate subsequent features. Step one, do the convolutions. We'll talk about what is a convolution. Apply filters, kernels. Oh, this is just like a weird language, weird lingo. What is a filter? What is a kernel? I'll talk about that in a second by showing an example of fixed size over the text to capture local and gram patterns. And then each filter produces a feature map. We call it a feature map, subset of the features. And then you can maybe combine those features together to get your eventual feature representation. This will highlight specific semantic structural patterns. Okay. Step two, you do some pooling. That is, you have like a large feature map, and the pooling will reduce this feature to get the significant ones among them. So select the most important features from each filter output. For example, could be the maximal one that is maybe the strongest. Could be the mean, maybe taking the aggregate of them or whatnot. You can do averaging pooling, averaging the feature activations across all positions. Example, given the feature vector from tentative deal reached, blah, 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 the max pooling selects the strongest signal from each filter for the sentiment. For example, this is positive, tentative deal reached, okay, to keep the government open. This is a positive sentiment, right? It's not a negative. Anybody? Me neither. But in general, in the general scheme of things, right? It's maybe positive or neutral. Let's say neutral, right? For us indifferent people, right? Indifferent. So what are the words that capture this indifference? Maybe a tentative. Well, I don't know. I mean, I want to get like I don't know. I want the government to be open. I don't know. So whatever that is, like, you know, a bunch of words that capture that. And so the idea that we have here is when I talk about next about like pooling and like how max pooling is done, then you keep in your head that in your mind that what we are referring here is that eventually the features that we are pooling are going to be the ones that are maximal to the given objective that we have. It's like could be that we are emphasizing only tentative, keep, and open. Okay, make sense? Okay, so that is like, you know, high-level concept, like scientific concept that we have, pooling or max pool or top K pool. This is what it translates to. So there is also going to be a fixed length representation of the sentence independent of the input size. This is very good because, you know, now your feature is no longer a book. It's going to be just like a vector representation of 256 values, and it's going to be the thing that you'll use. Can you imagine that? So like, what is this book? Is it like sad book or happy book? And can I classify the books like a whole book by extracting just a feature representation of 256 values, and I feed it into a classifier, and that's going to give me the positive, negative. Make sense? This is quite powerful an application. This is like the kind of application we should care about, right? Some of us, not all of us. So it reduces dimensionality while preserving the salient, like the hidden features, the not spoken features, improves the efficiency compared to RNNs, and does not capture long-term dependencies as well as attention mechanisms and transformers. This is good and bad. It's good in the sense it does not really cost you much. It's bad, it does not allow you more functions, right? But for our function, we don't care. All right, now. So this is a classic example. Yes, question.
Is there any larger cost to do CNN over RNN? Like, is one more expensive to run?
No, it's cheaper, always cheaper. Very, very cheap. Way cheaper. It's like 3 orders of magnitude like 1 to 1,000, right? Yeah, 3 orders of magnitude, 1 to 1,000 times. Yeah, it's like computationally this is faster. And you'll see like why, because what you're doing here is that you are collecting cheap features. So let's go over the mathematics here. The one-dimensional convolution of a sequence X with a filter or a kernel W. Now a filter, you know what it is, just like a small matrix that you slide it over your representation to manipulate this input, your initial representation. Okay, so just like a filter, you just like put that filter on to see something, move it to see something, move it to see something. Okay, and so the convolution y, the convolution by the way is this operator, the star. So y multiplied by xt here. Okay, you can imagine that x is going to be the input and y is going to be the filter. At any point t, at any time step t, is going to be the summation from I equal 0 to k minus 1 is going to be the kernel size of wi multiplied by x t minus 1. Nah, that's bullshit. We have no w. It's going to be the y. Make sense? The yi multiplied by x t minus 1 minus I. Make sense? Okay. We have no w here. I put w, but then I replace the w with the y. Okay. So you can see that x is going to be the input sequence. W is going to be the convolution filter. Y is going to be the output feature map, but does not belong in that place. Should not be moved there. And k is going to be the size of the convolution filter. And the convolution operator is going to be what we have here. Now, this is a little bit too much for most of you, for me at times. So let me give you an example and show you how it works. Okay? Forget about that. So let's say that we have x to be those values, 2, 3, 1, 0, 4. It's going to be the input. And we have the filter, w. There's going to be 1, minus 1, and 2. This is a filter of size 3. And so what we want to do is that we want to calculate the y's, right? The output. Okay. What is the y? So y, for the position of 2, t equal 2, is going to be what? Can somebody help me? Remember, the sequence starts with 0, right? Start with 0, 1, 2. So basically what we're saying here from this equation is that I bring the filter, this filter, on top of the input sequence at the index 2 and do a pairwise multiplication and summation. So it's going to be 1 by 1, right? This is what it is, 1 by 1. And then 0 by minus 1 and 4 by 2. This is messed up. Does it make sense? So does it make sense? So it's like, this is what it is. Just like this is the filter, this is the input sequence. What the filter means is that you just like put the filter on the input sequence where the index is. The index here is like the position is 2, t equal 2. You put them on top of each other. And this is what it's saying, is that it's just like saying you do the multiplication of them pairwise, wi multiplied by x minus I, and so forth. And then this is what you get. Okay, does not make any sense to you. Let me show that for you graphically, visually. Okay, this is 1D. Okay, so let's say that we have this matrix. Okay, so what I said is that this is 2D, not 1D. What I said is that you just bring the filter, put it on your underlying matrix, underlying like structure, the input feature, and then do pairwise multiplications and then summation of all the multiplications. In the case of 1D, if I'm starting from the beginning, then I bring my filter, a 3, size of 3, and then I put it on top of my input feature and then multiply pairwise, the first with the first, the second with the second, the third with the third, in the case of the 3, and then sum the outputs. And then I move my filter to the next place and do the multiplications pairwise and sum them, and so forth. How does that change in the case of the 2D? Here I have a filter of 3 by 3 and an input matrix of 5 by 5. Okay, this is 2D. Make sense? So how do I do the calculations? I superimpose my filter on top of my underlying feature map. My feature map was like 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1. Okay, and so forth. What I do is that I superimpose those values, and I put the zeros and ones because they are easy to calculate and verify. So my filter, like that I had originally, was 101, the ones in the red here. 101, 010, 101. Okay, so I put it at the like from 0, 0. I put it, and then I do the calculations, pairwise calculations. The 1 by the 1 is going to give you 1, then 0, then 1, 2, then 0, then 1, 3, then 0, then 0, 0, then 1, 4. Make sense? Anybody lost here? All good? You are lost. So I need something to point at with. Oh, I see. I have something actually. Okay, so this is our filter. The numbers here in red are our filters. You see them? Those are our filter. And this is the actual initial feature map. So this 4 came, I said, like, what is the convolution? The convolution is going to be like element-wise multiplication of the filter by the underlying input map. So 1 by 1 equal 1. 1 by 0 equals 0. This is 1. 0, 1, 0, 0, 0, 1. How many ones we had? 4 of them. So it's going to be 4. Let's shift a little bit now. So I'm not going to tell you about like all the magic. The magic is going to come later of like what are the parameters that we can use to control how quickly we can shift our filter on top of the underlying feature. There is like strides and there is like whatnot. Okay, so let's forget about them. Let's, for the sake of it, let's just like do another example. I'll come back to you. Do another example where we shift our filter by 1 step. So now the filter, the 101, is going to move to this block. Okay, this block. Make sense? So 1 by 1 is going to be 1. 0 by 1, 0 by 1 is going to be 0. And 0 is going to be 0. So we have 1 from the first row, right? The second one is what? It's going to be 1. The third one is going to be what? Also 1. No, not 2. Is it? It's going to be 0 here. So it's going to be 1. So this is going to be 3. Make sense? Your question. Huh? T is just like the stride, the position. Now, that's what I'm saying. That is what I'm saying. So like right now, T here equals 0. When you start to calculate the features using the filter from scratch, you'll assume that you're starting from 0. For any position, like, if I'm telling you like right now, the position is 0 and 0, start from here. But 0 and 1, you start from here. 0 and, 2 and 2, you start from here. So your filter is going to be covering this block, 2 and 2. So the output is going to be 2 and 2 is going to be for this one, for this last one. Okay, make sense? 0, 0 to 2 is going to be 9. Any questions? And this is like the output is going to be like, right? So the output is going to be for the feature map is going to be something like this. The input matrix, this is the input matrix, and then here's going to be the region extracted for that, and it's going to be the feature map. The feature map is going to be like here is going to be, this is -1 to 0. It's like in a representation. So you have like 3, the 3 that we calculate, this is 4. 3, the 3 was here, 4 was here. This one is going to be 4. This is going to be 2 without calculation. 2, 4, 3, 2, 3, 4. This is how you read this output. I did the calculation for all of them. Make sense? Good? Okay. All right. Any questions? Is it simpler than it is mathematically? It's simple, right? So let's go over some of the magic that we have here. And so for this, we will go back to our 1D. And so here, the first thing that we want to do is basically get the discrete convolution for text. And so let's say that we have the original data that we have, tentative deal reached to keep government open. And the initial vector representation of each of those words is going to be this vector. Where do you get this vector from? Say word to Vic, or maybe n-gram over the, I don't know, whatever, over the letters. Here is just representative. It is not like an example. It does not necessarily have to be accurate for what we are trying to do, right? It does not have to be real. So let's say that we have those features, and we have the filters or kernels of size 3. The width of that is going to be the same width as that of the filter. And then the height of it can be anything. It can be like of size 3, it can be 4, 5, whatever. Okay? And so the idea here is that what we want to do, because this is like a size of a 3, what we want to do is that we want to calculate a feature map for this sentence. Tentative deal reached to keep government open. Okay? How do that? We superimpose this filter on this data, on this input. So for TDR, we will have a single value. For the tentative deal reached, single value. For deal reached to, single value. For reach to keep, single value. To keep government, single value. And keep government open, single value. And you can go down. You can have like 0, 0, 0 under that, so that you can have a feature for open alone. So how do we calculate that? We just like superimpose this one on top. So the superimposition would result in the following value here. So if you put this one on top of this block here and multiply 3 by 2 and by 0.1 and 1 by 0.1 and then minus 0.3 by 2 and so forth, you will get this calculation. This is the exact calculation. How do you what? Choose the filter, learnable parameter. Okay? So you have like multiple filters that can work for sentiment, for whatnot, learnable parameter. Okay, makes sense? And so you get like, you know, for this one, TDR, for this like 3, for those 3 ones, if you get the feature, it's going to be -1. I did the calculation for you here. I mean, trust me on that. And similarly, we can do that for DRT, for the deal reached to. It's going to be -0.5, -3.6, -0.2, -0.3. Make sense? So eventually, for this whole sentence, instead of having like all this representation, you can have a simple vector representation. And this can be fed into your system to get you the sentiment out of it. Any questions? Scary? I mean, like, you know, when I look at you, I feel like, you know, everybody should be lost. What is going on there? Tell me more. It makes sense, right? Okay, so, okay. You should wear like black glasses, not to scare me. You have them. All right. So any questions? Is that right? I've been explaining to the people here. I'm going to explain here. Okay. And this way I will not be scared. So all good? Make sense? Does it make sense? If I get you like in your midterm, like an example like this one, and I ask you to do the calculations by hand, 0 1s, you'll be able to do it, right? Yeah, 0 1s. Huh? You know what? I'm going to give you some example of that. Don't take my word for it, but I'm going to give you some example for that in the exam. All right. So any questions? So again, you just like do the calculations. It just works wonders. Yeah. Nah, man, I'm messing with you. I'm not going to, like, this is a graduate course. What do you talk about? Come on, you scare me. So no. I'm not going to do anything that requires calculator. Okay. So this is good. This is useful. I can just like walk around. So the second one that we want to have is going to be the terminology that we use in CNNs. And the first term that we have, so the first one, like I use a lot of terminology there. I use filters, kernels, whatnot. So you understand what they are. But now, do we have to do that shift like step at a time? Like here, eventually I had a size of 1, 2, 3, 4, 5. What is this 5? The feature size 5. It is 7 minus 2. It's basically 7 minus the size of the filter plus 1, right? 7 is the size of the input feature map, the dimensionality of it, the height of it. Make sense? If I don't want to have like that much, if I want to have only like 4 of them or 3 of them instead of 5, do I have a choice? Yeah. So you can do some strides. We call it strides. Okay. Or you can change this filter size. If you have the filter size to be 4, then you'll lose 1, right? Or you can do strides. So what are those strides? Or you can do some batting. For example, you want to have more features, you can like, add battings, like you add zeros at the bottom, so that, and at the beginning, so that the filter is applied on everything. So it's applied on tentative alone with some prefix, and on open with some suffix. And because you do not know the suffix, you can add some batting of zeros, or whatever like identity value that you want to add. 0 is typically the right thing to do here. Okay, makes sense? So it's a filter, right? It's a filter in glasses. So at least like this particular part alone is being applied to the filter, or the filter applied to it. Yes.
That make it like faster. Oh, you're getting the answer quicker, but you're using more things.
It's going to make it slower, but again, this is just like a simple multiplication, so it's not going to be that slow. Yeah, it's going to be slower in the sense that to get any value, you have to do an additional row of multiplication. But not significantly slower, because you are going to lose one feature, right? You lose one. I mean, this example does not seem like to be different, but you'd imagine that it's going to be slower, but not big of a deal of slower compared to like deep neural network kind of slower, where you have to do some optimizations and multiplications. Okay. All right, so let's go over those terms very quickly. So the first one is batting. What do we mean by batting? I told you what it is. You add some like identity values at the beginning, at the end. How many of them? You can add as many rows as you want, depending on what you're trying to achieve. And so in this example, we added like this phi row, and it's going to be 0, 0, 0, 0. And then at the end, phi row, and we had 0, 0, 0, 0. Still, we have the same filter. And the way that it affects it is that, so you apply the filter on phi tentative deal, to get the feature representation of the first. And then at the end, you have it on government open phi to get a value from that. So here, instead of having 5 values, 1, 2, 3, 4, 5, 6, 7, you have 2 additional values, 1 for the prefix and 1 for the suffix. Make sense? And this is what we call batting. How many we can bat? We can bat as many as we want. Okay. The second one is called channels. Initially, we had single filter, 1 filter only. Now, it does not have to be 1 filter. You can apply multiple filters. So you can have filter 1, filter 2, filter 3. Okay, forget about the batting here. But what does the filter imply? It means that you add 1 additional column in the feature space for each filter. Make sense? So you apply this filter on top of, forget about the batting, on top of the original feature space that we have here to get a single value. This is minus, well, it was, I don't know, was minus 1, was minus 1 initially. And then you apply this filter here on top of this one, right, to get another value. It's going to be 1.6. And you apply this filter here on the same part to get 1.4 or minus 1. Make sense? Any questions? You can apply also the batting with the multiple filters. So you can add like, the batting here, and then you can apply those 1, 2, 3 filters on the same part to get 3 different values. Okay? Make sense? Why this is important? Why do we use multiple filters? You can imagine that some of those filters are built, like one of those filters is built to capture the semantics. Another filter is to capture, like to weight the syntax. Make sense? Another one can be for like, I don't know, other features like language features, like edge cases, like, we're talking about positive, negative. And so one of them can be used for eloquence. I don't know. Oh, why am I saying this? This is sentiment. It does not really make sense to care about eloquence or to care about semantics, because the same architecture can be used also for translation. And in translation, we care. In translation, we care about that. We'll talk about that when we talk about CNN-based translation. Any questions? So this is multiple filters. So you could use 0, variant can be 2, also called wild convolution for that case. This is like a narrow convolution, single value, and the wild convolution is multiple filters. Okay. Oh, this makes sense also more where this idea of CNN has originated. Where did it originate? In images, right? And images have like channels. So these filters are called channels. Make sense? So RGB, can use one for the red, for the green, for the blue. Okay. All right. What do we have? What else do we have? All right. So the next one is max pooling. What does pooling mean? Pooling in this context means that you calculate a feature from the feature map that you have calculated, and that's going to be the maximum, max P, the maximum value among those all. So what is the maximum among those? It's going to be 0.3. The maximum among those is going to be 1.6, and the maximum among those 1.4. There's going to be an additional feature that you add to your feature representation. It's called max pooling. You can use this one alone, individually, alone, or you can use alongside those. Make sense? Okay. What else do we have? Averaging over time. So you can do the total average over time. So the average of all those values, plus my calculations. So it's another feature. The average of those, this one, the average of those is this one. It's going to be called averaging over time. Okay. And you can use that as a feature alone or as a feature in addition to those features. Any questions? All good? Okay. Yes, go, please. The max is going to give you the most significant feature. So remember, what is this feature? What is this feature? What is this feature capturing here? It's capturing convolution for a given window. So it says to you, for this filter, the most significant window for the, like the previous slide, this one, the max, right? This is we talk about the max. So the most significant window was the KGO, the keep government open. That is the most significant window with respect to the convolution. Similarly, in this case, it was what? It was 1.6. So TDR, tentative deal reached, keep government open. This is one feature, this is another feature. It just tells you this is the maximum. It tells you what is the most significant one feature-wise. So you can relate that number back to the original inputs. What is the average? What does the average signify? What does average signify? It tells you with those filters, this is what is the shape of the entire sentence, entire sentence here, on average. Like the middle point, imagine that those are like points in 4D. So the middle point, like the single contraction point for all of them is going to be in this space. So imagine with that average is that you have a large number of sentences, so many of them, okay? So many sentences. It will be able to project for you the sentence in a space. This is going to be, here is on average the points, the different words as points, if they are like, getting the average of them, the central point for them in space is going to be here. Another sentence is going to have a representation here. And so if you are to separate those sentences with your classifier, you'll be able to do that, comfortably. Make sense? Because this is going to be your feature representation. So you are taking average of the sentence. The sentence is going to be a bunch of words. Each word is going to be a point in space, in geometry. And then the average is going to be an average of those points. It's going to be another point shifted somewhere in space. Make sense? Intuition is simple here. And this is like one of the beauties of CNN in this space. All right. What's going on there? Are you in our class? What are you coming here to do? So it's like only 10 minutes off. We are leaving soon. All right. So what else we can do? We can do strides. Stride. How fast you can just like cover the entire initial map with your filter. And so if we say stride of 2, it means that I take OTD, there's going to be OTD, and then DRT. So DRT. So this is like 0 and 1 and then 2. Like I skip that one, and then like I go to this deal reach to, so deal reach to, and then I go to I skip reach, so I go to keep government, and then government open phi. I'll be able to reduce the feature map size. What else we can do? We can do max pooling with stride. So now the striding is going to be over this one to get our max pool. So you can get the max of the first two values, like this is stride of 2, the max of the two values, the max of the next two values, the max of the next two values, and the max of the next two values. And here, because this is an odd number, an odd size of the feature, I just add like I bad here, because you want to average, well, not average, you want to take the max pool with a stride of 2, and for the last one you just like phi it. Okay, make sense? Questions? You can do k max pool with k equal 2 similarly. So that what does it mean is that you just like get the highest value and second highest, that is that 2 max peak, like it's called k max pooling, k max, like top k, top 2 with k equal 2. You can have the top 3, top 4, whatnot. You can reduce this feature. So to get like for those who work in machine learning, feature selection, the most significant features. So here you do not care about like only the most significant window, but the top 10 windows are most significant. So you can do like k pooling, k max pooling with whatever k that you want. Okay, so to get the features. Any questions? Are we good? Easy. All right. So let's go over how that works in real life. And this is what is called CNNs for synthesis classification. It's a work by Kim et al. In 2014. And so for those who work in this space as researchers, PhD students, you might feel like bad. This idea was published at some point in time, but this is like how science is started, right? It's very easy to understand, and the bar was very low. But right now they expect you to like build a rocket to be able to publish in those places, right? And so this is like a top research paper, very well cited. The idea is very simple. So it is by Yoon et al. It introduced convolutional neural networks for sentiment classification, sentence classification, sentiments, inspired by another variants by Colbert and Whiston. And CNNs effectively extract key n-grams, like the way that we described earlier. Applications are for sentence analysis, so can classify sentence into positive or negative. Unlike traditional methods, CNN automatically learns important features using the techniques that we mentioned earlier. Other applications for that could be subjective versus objective classification for a given text, determine if a sentence expresses an opinion or some factual information. How does it work? Well, other applications here is like, for example, question classification, categorizes questions based on type, person, location, number. You can capture phrase level meanings. You can work in parallel, unlike RNNs, and then you can be useful for short text classification. And the way it works is like this. So you start with your initial sentence, the country of my birth, and then you can use like this is the window classification. So this is the window, and then you apply the filter on that window to get the first feature, and then you just slide and get the next feature, and then slide to get the last feature. This is going to be your feature representation. The filter could be of any size, 2, 3, 4. And so this feature representation is going to be used for your classification. Make sense? So I mean, like I explained to you the way that you do it for all the way. Okay, so this is a mathematical expression of it. So what this particular work. So pooling was done max over time pooling layer. The idea is to capture the most important activations that we had, as explained earlier. From feature maps, you will be able to pool a single number, starting with C equals C1, C2, up to Cn minus H plus 1. H here is going to be the size of the filter. Use multiple filters. For example, you can use like 2, 3, 4 filters, and then you can get the max of those filters. It's useful for different widths of the given input, and because you are using max pool, so the length itself is going to be irrelevant, and eventual feature representation is going to be basically what you have here, and you just like feed that into your classifier. Okay. This is like the way it works from start to end. So feature extraction with CNN. You do the convolutions, get max pooling, you get your features. Then you flatten and get a fully connected layer. What is a fully connected layer? It's going to be RNN. So you might say like, David, oh, you are bullshitting us. Like at the beginning, you said we want to get rid of the RNNs, but now you are giving us RNN, right? A fully connected layer. Why that is not bullshit? Because we are not using the RNN for feature representation. We are just using it as a very simple, single, like the fully connected layer, single layer, not like the fully fledged deep neural network that is going to be very costly to train and maintain. Okay, yes. It's to smoothen things up. Yeah. So typically, like when you, bless you. So when you see like in any pipeline, when you see like a fully connected layer, it means that the features that you have are rough features, like what we call dirty and cheap features, and you want to polish them a little bit with respect to some loss, right? And then whatever output that you have, then you decode it. So you have like a feature that is beautiful, more or less, and then you can either decode the output or just like put it into a very simple classifier like random forest, and then random forest will decode for you the output. Make sense? Okay. So you flatten and pass through a fully connected layer. So the booled features from here are going to be flattened into 1D vector. Flattening a 2D vector is going to be how? Remember the feature that we had is going to be like, in the previous example, 4 by 3 or 4 by 7. How do you flatten it? You just like get the first row, but can connect to it the next row, the third row, the fourth row, and so forth. Flatten it. Make sense? Make sense? No, does it make sense? Okay. What does the flattening mean? Flattening means that you have this feature here. Like let's say this feature. How to flatten this 2D? How many of you know MATLAB? Yeah. So matrix to vector. So how do you matrix to vector? This is a matrix. So you get this row, and then after it, you put the second row, and then the third row, and then the fourth row. It's called flattening. Okay. So you flatten it. You make it from 2D, from two-dimensional, and you flatten it. This is the flattening. Okay. So you flatten it, and then what do? After flattening it, you pass it to the fully connected layer to learn the higher level representation. Remember that? Like the fully connected layer, what it does, you get like rough features and you polish them to get like a better representation. This was initial representation, cheap and dirty, right? And you want to get like a better representation. And then you put it in your classifier. The classifier could be just like a random forest classifier, or could be like, sigmoid or softmax or whatnot. And then the softmax activation is used for multi-class, and the sigmoid is used for binary classification, like positive, negative, or this one is going to be a question type or entity type or whatnot. Okay, so CNN extracts the features, fully connected layer is going to learn the pattern, and the softmax is going to make a final prediction. Make sense? Good? Now you can make your project about sentiment analysis. Not too late. 26th of the month is going to be the deadline for submitting your milestone. How many of you have invested some time into that?
Have what?
Invested time into their project. Like, raise your hand. Be proud of yourself. Yeah, it's very good. Very positive. So I expect like everyone will get like an A, because Mr. Hemeti, he's like slaughtering you guys with the assignments, right? I saw the deductions. Too much deductions, right? You agree with me? Yeah. So I'm the soft heart here. Just I'm not. Those who know me don't know that. But do something for the project, okay? And so what are the limitations of this one? So there are multiple things I threw under the bus, right? So limited long-range dependency. We mentioned that earlier. This is good or bad. We do not know. It depends on the application. Lack of adaptive attention. So unlike transformers, CNNs do not automatically weigh any different parts of the input, and increased depth of the large context. Make sense? We'll talk about the very deep CNN later, and we'll tell you like how we can solve some of those problems. What do we have here? RNN suffer from some problems. CNN try to solve them. Max pooling over time enables fixed length sentence representation. CNNs are efficient for representation. However, they struggle with some problems. And for large context modeling, transformers are kings. Okay? That's it. Thank you so much.